So I wanted to point out one small change I made to the syllabus to start things off with. I updated the paper copy that's printable right here so that it reflects our current version of the schedule of events, but I also changed it so that at the end of finals week, all work is now due by 5 o'clock. I had previously let it go to midnight, and for various reasons I need to cut it off sooner. So finals week, we are not having any classes, but I am going to hold office hours during all of the times that I would normally be teaching. So if there's any work that you need to finish up and need help with, that should be hopefully plenty of time to get everything together. So there's that. We have a quiz to go over today as our first topic, formative assessment number 3. And so I looked at these this morning. A few points of confusion here and there, but I think as usual, it's always helpful to go over it and make sure that we're all on the same page. So if you want to go ahead and pull that up, I'll start the first question here. So type 1 error. What Greek letter do we use to represent type 1 error?
Alpha.
Alpha, yes. Type 2 error has a Greek letter associated with it.
Beta.
That one's beta, although we also use beta for slopes, for fixed effects. So that one tends to be used less often, but alpha for sure is something that you will see referred to in written results. Alpha also refers to a measure of reliability, Cronbach's alpha as it's known, so that's a different use of alpha. They get reused, so that happens. The question is, what kind of decision could possibly lead to each type of error? So this was in reference to if you are making a thumbs up, thumbs down decision about the significance of an effect. So rejecting the null or not rejecting the null, what kind of decision would lead to a type 1 error potentially?
So you set an alpha too high, and then you reject the null hypothesis when there really is an effect.
Yes, so a type 1 error is a false positive. When you think you found something, but the null hypothesis is actually true. And you control the percentage with which that is expected to happen as your alpha rate. So what is our typical alpha rate in the social sciences? Yeah, finger question. I love it. Everybody's programmed ready. We got the finger questions locked and loaded. 05. What if you want to be conservative? What would be a more conservative alpha? Yeah, 1. Yeah, 1%, 0.01. So 1 time in 100, you would reject the null hypothesis when it's actually true. Yeah. What kind of decision then leads to a type 2 error?
It's a false negative. So you're saying something is not significant when it is.
Yes, when you have an effect in the population and you do not reject the null hypothesis, when you retain. Or more simply, you miss something. That's a type 2 error. So type 2 error conventionally in the social sciences is supposed to be what? Do you remember?
Is it 80%?
Very close. So power is 80%, which would make type 2 error what? Yeah, 20%, because power and type 2 error are the inverse of each other. So power is your probability of finding an effect of a given size. The probability of missing an effect of a given size then is type 2 error. So yeah, 20% is sort of the conventional level we're told to aim for. Good. So bringing up then, what is power? So a range of answers from you. What did you write down? How would you describe the concept of power?
I thought of it as the chance that we're right with our hypothesis test.
Okay, I'll take
I mean, I need to dumb it down for me, so that's what makes it stick in the old noggin.
Okay, so being right, then, if you want to like clarify what it means to be right.
That what we found in our hypothesis test was true.
That
I don't know. I'm gonna pass it along.
Okay, fair enough. No, You're definitely in the neighborhood. I'm just trying to get a little more specific language attached to those general ideas. So the idea of power is always in relation to a specific effect size. So then it's like finding what? Finding that. Like a correlation of 0.3 or a correlation of 0.5. You have a power for that specifically. So then power, if I have a correlation of 0.3, what's my power? We don't know what it is. It depends on sample size, right? But conceptually, like, what is power if I'm talking about a correlation of 0.3? Jerome, were you going to say something?
Oh yeah, I was going to elaborate on Alex's point.
Go for it.
I was saying the probability that we will correctly reject the null hypothesis and claim our result is significant, or the probability of not making a type 2 error since they're inversely related.
Yes, very well said. The probability of finding it if it's there is sort of the way that I conceptualize that. But yeah, the probability of rejecting the null hypothesis at a given effect size is your power, and then 1 minus that is your type 2 error. So there are 3 things that can increase your power. What are they? If you want more power, what should you do?
A high sample size,
Yep, more people, more power.
a greater effect size,
Yep,
and a higher alpha.
there it is. So yeah, higher alpha is tricky though, because if you make a higher alpha, then what are you saying is more likely to happen, or what are you allowing?
More type 1.
Yeah,
Error.
type 1 errors. So if you make it easier to declare significance, then that has a benefit of increasing your power, but at the same time, it's sort of a false benefit. So I wouldn't recommend that as a general strategy, but increasing sample size, and generally speaking, if you have a higher effect size, you'll have more power to detect it. Several of you wrote down things related to residual variance or variance remaining. And I tried to correct that in your answers. It's really about the effect size. So if you think about variance, it's any given variable is going to have some variance associated with it. And less variance doesn't increase your power per se. Less variance increases your power so much as it's a consequence of there being a greater effect size. So less variance left over occurs when you have a larger effect size. But it's really about effect size and not the amount of variance per se. So we'll talk more about ways of operationalizing how effect size relates to variance today, actually. So that's coming down the pike.
Lisa, can you do me a favor? I realize I should probably know this, but can you just remind me what is effect size? Like, what are we talking about when we say effect size?
Yes. So I just turned on the transcript there, which means I got to block the camera. There we go. Effect size is the strength of a relationship between 2 variables so far in a metric that is readily interpretable. So it's an absolute type of effect size as opposed to a unit-based. So you know 2 different instances of effect size so far. Correlation as a scale for an effect size where you know that it can't be outside the range of -1 to 1. And so if I tell you that I have a correlation of 0.3, you know immediately what that means. If I said, oh, that corresponds to a regression slope of 8.2, you'd be like, 8.2 what? Like it's not directly interpretable when it's scaled in units. So effect size is a way of taking a relationship that has units as part of it in terms of describing it and putting it onto a standardized way of talking about it. So correlation is one instance. D as a measure of standardized mean differences is another. That one is not bounded, but it's in standard deviation units. So if I said I have a D of 0.5, that means that I have 2 groups and the means of those 2 groups differ by half a standard deviation.
Okay, thank you.
Great question.
We talked about this. I just couldn't get there, so thanks.
No problem. It's interesting because sometimes effect size is directly what you get out of an analysis, and sometimes you have to take extra steps to convert what you get into an effect size. So when we did Pearson correlation, right, the correlation is the effect size, the end. But where correlations came from, like one step in the computation before that was covariance. Because we start with mean and variance of each variable, compute covariance, which is how far above the mean you are on X times how far above the mean you are on Y. And that is in units. And so then we standardize that by dividing by the standard deviation of each of the two variables, and that gets us to correlation. So when we did correlations, you get the correlation directly, you get your p-value, the end. Then when we did chi-squares, the chi-square is a test statistic, which is a function of both effect size and sample size, but you can back translate a chi-square into an R or into a D. Now we're in the world of regression slopes, which are measures of a relationship that are unit specific, and we have to take an extra step to convert that unit specific slope into a measure of an effect size. So standardized slopes is one way of doing that, or taking the t-test statistic for that slope and converting it into an R or a D is another way. So great questions. So in terms of being able to predict power, power is related to replicability. So I can give you kind of a real world example. Like I used to be involved in track and cross country in high school. And I was one of those runners who would run better in practice. Like whenever I had a meet, I couldn't get out of my own head. And so like, even though I was capable of running, say, you know, a 5:30 mile or something, the probability that I could like pull myself together and do it when I needed to is much lower. So you can think about like somebody who, the opposite of me, who runs very badly in practice but can pull it together through the meet. Like they may have a very low probability of actually hitting their target because they don't have that, like the target is too far away from where they would normally be. Whereas like if you know that you can consistently run at that pace, you can do it in a meet, you have strong power because across replications of meets, you would be predicted to hit your target most of the time. So power is related to replicability in that if you have a lot of power, you would expect that the effect would replicate across samples. If you happen to find a significant effect that has low power, that means by definition it's less likely to replicate because you were only supposed to find that effect, say 10% of the time. The other 90% of the time you wouldn't be expected to reject the null hypothesis for that combination of effect size and sample size. So power is one of those things that's very helpful to pay attention to. If you're going to plan a study, someone will ask you to do a power analysis. I can almost guarantee it. So that's one of those things that in each type of model that you learn, as part of the process, you would learn how to try and anticipate what power might be for a given type of design. So other questions or thoughts on that one?
So something I'm wrestling with, and perhaps you've covered this already, but between type 1 and type 2 errors, is one better or worse than the other? Because I'm thinking like, you know, if you've already got a procedure or something that's pretty good, like, and you make a type 1 error, all right, maybe not the end of the world because your baseline's okay, but you miss out on something that's an improvement. But, you know, alternatively, you know, if you have a false negative and you're out there using something that, you know, really doesn't have an effect, or in the alternative is bad, that seems worse to me, but maybe I'm not conceptualizing this appropriately.
I think that's a great question. I think that it really is discipline and context specific, which type of error is worse and how you would want to design your study to prioritize one versus the other. You know, you can think about the ramifications, say, of COVID tests, right? Like what is more detrimental if you take a COVID test and you have a false positive, meaning maybe you stay home for 2 weeks and you didn't have to, versus a false negative where you think you're okay, so you go out and wander the world and you accidentally infect someone else, right? Like in that context, false negative definitely worse. Think about the justice system. False positive of an eyewitness identifying somebody as committing a crime when they didn't do it. Way worse, right? To send an innocent person to jail potentially than maybe to let a guilty person go free. It just depends on the context, I think. So I don't know that there's an easy answer. Part of the problem with type 1 errors is that you don't know when you're making them. So there's been a lot of A lot of concern about effects that never replicate, because the first one to report a given effect maybe got lucky and reported a type 1 error, but nobody knew it, and so they started this whole field and people designed research to try and pursue this effect that never should have been there in the first place. So that's where like the intersection of type 1 error and power and replicability is becoming increasingly important as something to think about. But I hate to punt on the answer, but I really do believe that there is no black and white which one's worse. They're both bad in their own ways, and just making sure that you're aware of the consequences if you make one decision versus another. So that's all I can say. All right. Other questions? Yeah, go ahead.
So for raising statistical power, you could technically use voodoo bullshit to do it, right?
Yes, I was glad you mentioned that. I did see that in your answer. Yes, so voodoo bullshit, by the way, is the use of a one-tailed test as opposed to a two-tailed test. And I think you're running the risk then of conveying your result in a way that is, what's the word I want? Not dishonest, but kind of dishonest, right? If you have a one-tailed test that you expect a treatment to improve outcomes, then you're putting all of your area on one side of the distribution. But what if you find your treatment made people worse? Well, then you can't say that, because a one-tailed test does not allow for that possibility. All you can say is they didn't get better. And they didn't get better, to me, is not the same thing as they got worse. So I hesitate from a philosophical standpoint to say that a one-tailed test is okay, because you never really know which way it's going to fall out. That's because I'm in the social sciences, where we don't have the benefit of certain levels of precision of measurement, or like there is in physics or chemistry or other places where maybe a one-tailed test is a more reasonable thing, because like physically something can't happen the other way. But in my world, we don't have that level of certainty. So I would not recommend a one-tailed test as a way of increasing power, in the same way that I would not recommend increasing alpha as a way of increasing power, because you got to pay the price then on the other end in terms of a higher likelihood of type 1 error. But you are correct that technically speaking, that is another way to increase power, is to functionally, if you have a one-tailed test, then you have an alpha of 0.1 instead of 0.05. Because you've moved all of the area into one side of the distribution. All right. Other thoughts, questions? All right, last question. Definitions. You guys all nailed this. I was so pleased. All right, am I lagging? No, I'm okay? All right, I hear the rain picking up outside, So yes, and these three definitions, if you can keep these three things committed to memory, this will help you in all areas of statistics, not just this class, but in all models, because these three definitions do not change. An intercept is always the expected outcome when your predictors are 0. The slope is always the difference in y for a 1-unit difference in x, and a residual is always the discrepancy between what the model says the outcome should be and what it actually is. Those three definitions always hold in every type of model, in every type of sample. So those will help you if you can keep them in your head. So, all right. Any other questions on this quiz? All right. Any homework questions? I have homework 3 pulled up. That's our next task to complete before next Monday. No questions yet? Homework 3?
I may have a few for you in office hours later today. I just need to revisit what those are.
Okay, that sounds good. My office hours today should not be busy because the other class does not have a homework due right now. So they're all caught up, which means that I will be less popular than usual. So, all right then. Let's see. I have lecture 4 pulled up here. Tell me what you remember from last time. There, something a little better to look at while we jog our memories. What did we start talking about last Thursday?
we talking about models?
We were.
Okay.
Although I'd say that that's that will be true of every class. But we were creating new predictor variables to put in a model. Do you remember that? No, maybe?
I think we had maybe moved past like the empty model. It was like the next step past that. We were trying to make sense of like how they work then. But I don't remember the terminology very well, but I think I remember that.
Yes, you do remember that. So we had empty model as the baseline. And then in lecture 3, example 3, and homework 3, you get to practice adding in one predictor at a time. So it would be one slope to describe the linear relationship of a quantitative predictor with a quantitative outcome, or one slope to distinguish two groups for a binary predictor. So we are moving on past that to discover how to include predictors that require more than one fixed slope to fully delineate the way that they are related to an outcome. And so the instance we started talking about was categorical predictors. So if I have my nominal variable, for instance, whether or not your favorite TV show is Peppa Pig, PJ Masks, or Paw Patrol, if I want to know if that is related to the number of pleases heard, for instance, can I just throw that into a model as is? Nope. Can I ask SAS to give me a Pearson correlation between those two variables? You can, and it'll give it to you, but it's garbage. But we started talking about a strategy by which to represent, say, a 3-category variable as a predictor. Do you remember what we have to do?
It's
Like-
dummy coding.
Mm-hmm.
The columns, right?
Yeah, the columns. So we essentially have to create a series of binary predictors to represent each possible difference of one group relative to a reference group. So if I have 3 groups in my predictor, I need 1 fixed intercept and 2 fixed slopes, and those 3 fixed effects in total will perfectly distinguish my 3 means. If I have 4 groups, which is what you'll have in your next assignment, then I need 1 fixed intercept and 3 fixed slopes, and those 4 fixed effects will fully distinguish the 4 group means. So then it's just a question of figuring out which means and mean differences are given directly by the model and which can be found subsequently as linear combinations. That's what we were talking about. That sound familiar? Maybe? Ish? Do you want to go back over the columns and all of that? Yes? Okay. Yeah, it was 5 days ago. So, in all fairness, I couldn't remember what day it was, but then I remembered that we took the garbage out this morning. And so then I knew it's Tuesday, which means it was 5 days ago. So we were talking about making the columns, as you said. This is slide 5 of lecture 4 here. So the example that I'm working with is predicting annual income in thousands of dollars from a 3-category predictor of self-reported working class, where respondents could choose to be either lower class, middle class, or upper class. And to represent this categorical predictor in the model, I first have to create 2 new binary predictors. And the coding scheme here, this is known as dummy coding or contrast coding. This particular coding scheme makes one of the groups the reference and then gives me the mean difference for the outcome for each other group relative to that reference. And so it's up to you who the reference is. You can make it whichever group you want. In this case, I picked the lower class group because they were first and because they had the most people. So that seemed like a reasonable thing to do. It doesn't actually matter who the reference is. It's all about the interpretation of the model parameters that results from your coding. So I know that my lower group is going to be my reference because they are the group coded 0 in both of my new variables. So I am setting it up so that the intercept of the model, the expected outcome when all my predictors are 0, the intercept is going to give me the mean outcome for the lower group. Then in the first column here, which I've named L versus M, I give the middle group a 1 to distinguish them from the other group. The upper group, which is irrelevant at this point, still stays with a 0. And then in the second column, L versus U, the upper group is then distinguished with a 1. And we have to have both of these new columns in as predictors simultaneously. Otherwise, what happens? Fayaz, I'm going to call on you because you've seen this play out. What happens if I forget one of these?
Then I don't get the results I want.
Yeah, so if I forget the first one, what does my second variable then give me? This column all by itself.
Is it just the third one?
It would be how the third one differs from the combination of the other two.
Okay.
Because it, like internally, it doesn't know that these are two different kinds of zeros. Because they're not. So if I just put in this predictor by itself, it's not low versus upper. It's the average of low and middle versus upper. And so then that's the job of the other predictor, is to distinguish the two that were lumped together. So the first predictor then distinguishes low versus middle. The second predictor distinguishes low versus upper. And the net result when both are included is that they each are interpreted the way that we had intended. And yes, software will do this for you. I'm deliberately not showing that to you because I want you to be able to create this architecture yourself, and because it comes in handy a lot of the time to set up the model in exactly the right way that gives you the answers you're looking for in terms of who's the reference, what the contrasts mean, and so forth. And so here's what the code would look like that builds these two new columns in SAS at the top here and Stata at the bottom. In each case, we are setting up brand new empty columns. So the dot means missing data in both of these programs. And then conditionally filling in the empty columns based on the value of the original group variable, which is work class. So if work class is 1, then the new columns get filled in with zeros. If work class is 2, then the first column gets a 1 and the second column gets a 0, and so on. So this strategy then ensures that only values are filled in that match each of these three conditions. If I had a work class equals 4, then the two new columns would stay blank because I didn't address that situation in here. Okay, any questions on the setup for these then?
I have a question, Lisa.
Sure.
So do you recommend overwriting the original column?
No.
Create? No, okay.
No, 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 ever, no, no, no.
Okay.
Now, what if you do that accidentally?
I did that. That's why I'm asking. Yeah.
So, but that's okay, because in each of these programs, the original data that I'm giving you is an Excel spreadsheet. So your first step in the code is to tell it where your sheet is, have it read it in, it converts it to a SAS dataset or a Stata dataset. If you screw up and overwrite the column, okay, just rerun the code where you bring it in again, and it's
that's what I did multiple times, and that's why I was asking if that's the situation.
Yeah. And I have written the code to be able to recreate the database as needed in case you do something incorrectly.
So I'm asking. Oh, go ahead, please.
Yeah, I was just going to say in SAS. That is also why I am having you read the data into what's known as the work library, which is a temporary directory. You can read in SAS datasets directly into SAS, of course, but I always read in the SAS dataset from the permanent place where it's stored on my hard drive into the temporary directory, and then I do my manipulations in the temporary. That way, if I do screw it up, it doesn't overwrite the right copy on my hard drive, which I have done. Would not recommend.
So I asked this question because when I was working with a different data set, I had 74 columns because I created new ones every time I did something to a different column. So that's why to make, to ensure concision, I was asking if I should overwrite, but I should not.
I would never overwrite the original data, but you also, I'm also not in the habit of saving the results of those manipulations. So like I would save the original data and I would save the code that makes the 74 columns. I would not save the result of the 74 columns, because all you would need to do is rerun your syntax and they'll pop right back in again.
Okay.
So the end results of your manipulations don't need to be saved unless you need to send the data to someone else to do something with. That'd be the
I
exception.
get afraid that I don't have anything tangible, and what if the code doesn't work? That's why I just keep, yeah.
I know it's like an anxiety thing, but no, believe in the code, man. Believe in the code. Although, of course, in R, you know, things could stop working because someone updated their package and blah, 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 blah. But there are ways to solve that problem as well. I'm trying to remember what they're called, but there are ways to sort of like download like which package it was as part of your code, so that you don't accidentally like use an updated version of the package that makes it incorrect. So version control is a big thing in R, less so in the other programs. So. Okay, other questions or comments on this? So I want to point out that this set of zeros and ones is totally up to you. You control who the reference is and what each of these variables represent. And I'm going to show you in this lecture 2 or 3 other coding schemes that not just for dummy variables, but for continuous variables as well. And just to give you sort of a flavor of how you can set these things up to directly address each type of hypothesis that you have about group differences. So there's not one right way to do it. There's many equivalent ways. It's just all about convenience in terms of who the intercept is and which group contrasts show up as model parameters directly. Okay, so then in terms of the model, do you want to go back through this? What the parameters mean? Or do you feel good with this? Feel good? Or go over it again?
Can you go over it again, Lisa?
I see both answers, so that means I go over it again. In this case, we have to have let's see, here's the model. So the grouping variable, the 3 category variable, is the only predictor in the model. And I have 2 new slopes that I'm going to ask to be estimated for those, beta 1 and beta 2. So those are fixed slopes. They are constants that will be estimated as part of the model and will apply to everyone's scores equally. So there are 6 things that I might want to know about this variable. Because there's 3 groups, I might want to know what the outcome mean is for each of my 3 groups, and I might want to know pairwise which groups differ from each other. And there's 3 possible differences among my 3 groups. 3 of these are going to be given directly as model parameters, and the other 3 are given as linear combinations of the model parameters. And I have the dreaded unstable message. Can you hear me still? Good? Okay. Not that unstable then. So if I have the 3 possible group means here, and then the 3 possible differences, the fixed intercept beta 0, once you do the math to fill in the zeros and ones for the 2 columns for the predictors, the fixed intercept is going to be the group low outcome mean. That's what it's going to mean in this case. That's how it will be interpreted. The other 2 group means are going to be linear combinations of the intercept for the low group plus how the middle group differs. Beta 1 is how the middle group differs from low. Likewise, the mean for the upper group is given by what the mean is for low plus how the upper group differs, which is beta 2. So the beta 1 and beta 2 are differences. Beta 0 is the mean for the reference group. Given that the model does tell me what the mean is for each group, the model also then tells me what the mean differences are as linear combinations. 2 of the mean differences between the reference group and each of the alternative groups are given directly as the slopes. Beta 1 is how far off the middle group is from the low group. Beta 2 is how far off the upper group is from the low group. And to get to the missing difference between the alternative groups, that's a linear combination of the slopes. It works out to be beta 2 minus beta 1 is how the model tells you how the upper group differs from the middle group. So any of these parameters that are directly given by the model, beta 0, beta 1, and beta 2, those are going to show up by default. Any of these extra terms that are linear combinations, you have to ask for specifically, and I'll teach you how to do that. That's estimate statements in SAS, so things that look like this, and lincom statements in Stata. So we'll go over the code to do this as part of example 4, but that's in here also for your reference. And then these were the results. So I will show you how to make the software give you all of these numbers, but it works out that the intercept was estimated at 13.65. That's the mean for the low group. The slope beta 1 was estimated at 8.8. So that means that the middle group is higher in income on average by $8.8 thousand. The slope beta 2 was estimated at 10.98. So the group that's upper is higher than the reference low group by about $11,000. And then the difference between these two slopes, beta 2 minus beta 1, that's the linear combination given at the bottom here. And that's 2.13, which happened to be non-significant. So the upper group is non-significantly higher than the middle group by 2.13. And on the whole, the residual variance, the E variance before we put the predictor into the model from the empty model was 190. It became 171 afterward, suggesting that group does predict income because the amount of unexplained variance was reduced from 190 down to 171. And I think, yeah, and then we had a picture. So this is trying to describe the idea of the slope in a rise over run kind of way, where the group dummy codes are the x-axis, so lower versus middle as one x-axis, lower versus upper as the second x-axis, and then I have the triangles here to describe the rise in x for the run, or the rise in y, excuse me, for the run of x, change in y for a 1 unit change in x. And so then the difference between the two slopes is given right here as beta 2 minus beta 1. And I think that was where we left off, if memory serves. Okay, questions on any of that, or any of that you want to hear again or differently?
I have a question. So in our previous examples that we've done, whenever we've seen the sign change or the significance being there, it also let us know like the relation or the correlation to another like trend. I guess that was there too. Well, I'll stay tuned. I don't want to ask a question now. I'll just keep going. Because I was just going to say, will we have like anywhere within this where we're also getting like the correlation between like, oh, if this goes up, then this goes up or anything like that. But I could be not paying attention to something that's really key within this, or it could be to come.
I think I understand your question, so I'll try to answer the question I think you just asked, and you'll have to tell me if you did not ask this question. So the idea of a correlation, as x goes up, y goes up, that is in this, although it's just a little bit weird to think about it in this context. As x goes up is the shift from 0 to 1 in these binary variables. So as x goes up means as you switch from the lower group to the middle group. So the fact that all of these slopes are positive, beta 1 is 8.8, beta 2 is 10, means that as x goes up, meaning as you move away from the lower group, the predicted y goes up as well. It goes up by 8.8 if you're talking about middle relative to low. It goes up by 10.98 if you're talking about upper relative to low. So the key idea here is that to fully describe how working class as a variable correlates with income, you can't do that in only one correlation. It takes two, because we have to break up working class into binary pieces to be able to describe how each piece relates to income. And once we have the two, the third is determined as a linear combination. So there are actually three separate correlations implied in here, because the one that's in between the two refers to a shift from middle to upper as a third correlation. But it's a linear combination, so once we have two, we can get the third. All right, that's what I think you asked. Is that what you asked me? Okay. Glad to know I'm not totally off my game. Okay, other questions? All right, then taking this idea and adding on a new piece. So this idea that to fully describe the relationship between these two predictors, it takes more than one slope. We want to be able to combine those slopes to be able to talk about their joint significance as an index of how good the model is. So this is our first instance in which a model and a slope don't have a one-to-one correspondence. Our model at this point has two slopes in it. So if we want to talk about how good the model is, that is the same thing as saying how much does working class predict income. So we need to find a way to unify working class as one idea, even though it takes two slopes. And so I'm going to introduce the idea of significance testing for a model, not just per slope, but for the model as a whole, to describe how the predictive effects start working together to build an outcome for each person and how good of a job that combination of effects does. So that's where we're headed. So we can answer the relationships about how each working class group differs from each other in the way that we just described. So in this example data, beta 1 was significantly greater than 0, which means that the middle group and the lower group are different. The middle group is higher. Beta 2 was also significantly greater than 0, which means the upper group was significantly higher than the lower group. The difference between them was not significant, meaning that the middle group and the upper group are not different from each other. So their differences was within expected territory. But we want to be able to answer the question of how good does the model do across these two slopes and the third that's implied as a linear combination. Another way of saying it is, does the y hat that ends up being predicted by this combination of three fixed effects, the fixed intercept beta 0, the two fixed slopes, does the y hat that ends up being created by these beta fixed effects significantly correlate with the real y? That's what we want to know. So that's the same, another way of saying that is that we want to have a significance test for the model. How well does the model predict y hat? Okay, with me so far? That's the big picture idea. Another way of saying the same thing is whether or not the amount of variability that we had in the empty model has been reduced significantly. So in the numbers that we had for this example, going back, we had a total variance in income of 190. That's all the variance that there is to be had in this outcome variable. It went down to 171. Is that good? Is that a significant reduction, or is that well within expected territory? So the new thing that we're going to start talking about is how to assess the change in the residual variance, which is equivalent to saying how well did the model do in predicting y hat as it relates to the original y. Okay. So this is your first instance of a more general procedure known as a multivariate wald test. More generally, it's the idea that you can lump together a set of slopes to answer a question as to whether they contribute jointly to a model. So this is the first instance of this. There'll be others across the semester. So we have to be able to quantify how good these slopes did as a set in the context of a model relative to how much information they captured relative to how many slopes it took to capture that information. So we're bringing back into the conversation the idea of degrees of freedom, and there's two distinct kinds. There's numerator and there's denominator. So in answering the question, how good did my model do? How well is the y hat that's predicted by the model, how well does it correlate with the original y? I need to know how many slopes it took to get to that level of prediction. So in our current example, we've got 2. Because we have a 3-category variable, it takes 2 slopes to distinguish the 3 categories. If I had a 4-category variable, how many slopes would it take instead? 3 slopes. You're going to get to do that on your homework. If I had a 5-category variable, how many slopes would it take to distinguish? 4 of them. Yep. And it's always one less than the number of categories because you already have the fixed intercept that directly gives you the mean for the other one. So it's always number of groups minus 1 is the number of slopes it takes. So in these tests, numerator degrees of freedom is going to be the number of slopes that you are linking together that you want to get the test for. So k is the total number of fixed effects. K minus 1, the minus 1 is because of the intercept. So it boils down to just the number of slopes. The degrees of freedom for the denominator of this test refers to how many slopes could you possibly have included. That's a function of sample size. So degrees of freedom for the denominator is the number of people in your sample minus the number of fixed effects you've already spent. So in this example, I have 734 people. I spent 3 parameters to get to this level of prediction because I have a fixed intercept beta 0, beta 1, and beta 2. So that means that I have 734 as my n minus k, which is 3. That means that I could have 731 more slopes if I wanted to. So degrees of freedom is like, what's still out there to be captured? And in terms of the information to be captured, this is going to be a term known as sums of squares, and you've already seen this as the numerator of the equation for building variance. It's the idea of how far off is something from something else squared. And there's multiple kinds of this, which is why I'm being deliberately vague in my wording. So sums of squares refers to the numerator of the variance equation. So you know this one, for instance, just how do I get the variance of a variable to begin with? It's the outcome for each person, y sub I, minus y bar. Do you remember what y bar is? It's been a few weeks.
Was that the, I want to say mean?
Mm-hmm.
Nice.
Yeah, the sample mean. So this is the formula for variance. How far off each person is from the sample mean, square it so that the positives and negatives don't cancel, sum it up over people. So that's why this is called the sum of the squares, is because the term in here is squared. But this quantity, y sub I for each person minus the mean, that's all of the variability, all of the information that there is. So I'm using the term information because we're focusing on just the numerator part. We're not dividing by n minus 1 to turn it into a variance. So this is like all of the information that there is in this variable. And what we need to do is carve it up into 2 parts. How much of the information has been captured by the model? So how much of the information is included within what we're going to call y hat for the predicted outcome? And then how much is left over in the residuals? And so we want a ratio of how much information we got over how much information remains. That's where we're headed with this. So each piece of each section, so to speak, the information that's been captured by the model versus the information that's still out there, each of those has to get weighted. And so that's where the degrees of freedom come into play. So quantifying the relative size of the contribution. So how much information did the model capture per slope it took to capture it? That's going to be one quantity that we pay attention to, and that's what's known as a mean square, because we're taking the information captured by the model and dividing by the number of slopes. So it's kind of like information per slope. So it's a mean of sorts. And by information captured by the model, I mean this quantity right here. So the y hat sub I in the red minus the mean. So y hat is what the model says your outcome should be. So in this context, it would be the mean income level based on which group you're in. So everybody from the same group would have the same y hat. We then subtract from it the mean of the sample. So the idea here is, okay, how much better did we do by building a custom y hat using predictors than we would have done just giving everybody the same guess as to what their outcome should be, the mean. So the mean is like the worst you can do, right? That's the prediction from the empty model. how much more information have we captured by giving each person a y hat based on the predictors in the model rather than just the mean. Then we divide that quantity by how many slopes it took to get to that level of prediction. So mean square is like how good the model did divided by how many slopes it took to get to that point. Okay, how we doing? A thumbs up from afar. And some concentration faces, I think. Is that what I'm seeing? Concentration face? Or just sad face? One of the two. They look a lot the same. So then the other part of it. What's left? Well, how much information is still in the outcome variable that we don't know why it's there? So that's what y actually was minus the y that was predicted by the model y hat. So the term inside the parentheses, you know this term as a different name. What's another way of describing this term that's in the parentheses, y minus y hat? It was one of the terms on your quiz today.
Is it the residual?
That's the E residual, exactly. So what we're asking about is the amount of information still contained in the E's that's left over. And then, okay, well, how much information is left over and how many slopes are left over that you haven't put in your model yet? So then this term, information left over divided by the number of slopes you could have put in the model, that becomes something called residual mean square or mean square error. And that is the same thing as what we know of as residual variance. So the top part of this is mean square model. How much information in the outcome did your model capture per slope spent? The bottom part here then, mean square residual, is how much information is still there in the residuals per slope you could have added but haven't yet. So the per in each of these is degrees of freedom. Per slope is numerator degrees of freedom. Per slope you could have added but haven't yet is denominator degrees of freedom. And so then that gets you to a table that looks a little something like this. So this is the table that shows up on your output that I said you didn't have to look at yet previously. I said, just look at this one little square right here, and that's going to be the first question I ask about in your homework. Now we have to pay attention to the rest of the table. So we have three sources of three sources of information in our outcome variable, which is income in this example. We have information that's been captured by the model, that's the model row. Information that we still have in the outcome variable that we don't know why, that's the residual row, and then the total is the sum of those. So this table then provides a way to operationalize how good the model is doing. So we have the sums of squares for the model, so that's like the information that's been captured by giving each person a y hat rather than just guessing the same sample mean for everybody. How much better did we do by giving them a y hat? Then we have how many slopes did it take? And then we get mean square model, information captured per slope. Residual, okay, what's left? So this is how much information is in the E's, the discrepancy between your real outcome y and what the model says y hat. How much information is in the E's divided by how many slopes you could have added that you haven't. And so that gives you mean square residual, which is your residual variance. And so then the corrected total here is just the total y minus the mean. So these sums of squares model, sums of squares residual, sum to sums of squares total. And we do all of this to get two pieces of information that you would then report: a significance test and an effect size. So the purpose of this table is to quantify how good your model is. Is it significantly good? And how good is it in terms of an effect size? So R square is going to be our effect size. So do you remember R? We talked about an effect size like 45 minutes ago or something. Can you guess how r and r squared are related?
Square root is r.
Ding. For whatever reason, r squared gets capitalized. I don't know why, but that is always the way that it is written. But yes, r squared is r squared. I say that because you already have a concept of what r is. R squared is calculated using the amount of information in total of the variable minus the amount of information left over divided by the total. So r squared works out to be the proportion of variability that has been captured by the model. Of the total amount of variation in an outcome, what proportion of it has now been put into y hat, and what proportion of it is still in E? R squared is the proportion that's been explained, that's part of y hat, instead of the E part. Another way of talking about R squared is that if you computed a y hat for each case, and you have the y that was actually in the data, and you ran a correlation between them, that correlation squared is R squared. So R squared you can think about as proportion of variance, what proportion of variance was explained by the model, or you can think of it as the squared correlation between the y hat and the y. Two different ways of saying the same thing. That's an effect size. We can get a significance test for that R squared by taking the mean square for the model and divided by the mean square for the residual. So the ratio, what you know over what you don't know yet, is the idea. And that ratio forms a new test statistic known as F. So that's the last one we have to meet this semester. F needs degrees of freedom in the numerator, the number of slopes that went into it, and degrees of freedom in the denominator, number of slopes that remain. And F is a test statistic like chi-squared that is squared. So that means that F will always be positive. Worst case scenario, sort of theoretically, the lowest that F can be would be 1, meaning that you don't know any more than what you don't know. It's like a 1, it'd be like chance. I have seen F's below 1. Like you can actually do worse than chance, but 1 is sort of the theoretical lower bound. So F will always be positive. And that makes sense because what F is doing is linking together multiple slopes. So you want to talk about how the slopes work together to create a predicted y hat. One of those slopes could be negative and one of those could be positive, right? You don't want those to somehow cancel. So everything is in squared units so that that doesn't happen. So F you can think of as a transformation of R squared. So there's a formula right here for that. Or you can think of it as a ratio of what you know to what you don't. And it's a significance test for the model. So F gives you a p-value that allows you to answer the question, did we explain more variance than is expected by chance? And is the correlation between y hat and y significant? That's what F tells you. Okay, how are we doing? Good?
It's level, okay, question quick, is when it's telling us whether or not it's significant, is that still tied to the same sort of like alpha that we've done in previous models, same kind of thing?
Yep. If the p-value that goes with your F is less than your alpha, it is significant.
Okay. But we just would need to pay attention to the fact that it's like squared.
Mm-hmm. Yeah, that means that you can't look at the sign of it and know which way the relationship goes.
Okay.
Because it's summarizing more than one relationship. That's the whole idea here, is that F is testing a collection of slopes.
Okay.
Each of which could be positive or negative, and that's why everything has to be squared to make the math work.
Got it. Okay. Thank you.
Mm-hmm. And the reason that I told you before that we didn't have to pay attention to this table was because in lecture 3, example 3, and homework 3, you had one slope in your model. So for instance, in homework 3, you will examine the extent to which pleases heard predicts fits thrown, I think. Is that the way I did it? Does that sound right? and the extent to which age predicts fits thrown. So each of those relationships can be described by one fixed slope. So if you test whether or not that one slope is significant, and that is done by what kind of test? What's the letter that goes with the significance decision for a slope?
T.
T, yeah. It's almost T for everything. So T is a good guess. Yeah, so if you have a T that is the slope estimate divided by the standard error, that gets you your T. Here's the thing. If you only have one slope in your model, if you take that T and square it, you get F. If you only have one slope, degrees of freedom for the numerator equals 1. The t-test statistic for that slope squared is the F for the model. So if you don't have to lump together more than one slope, you don't need to do this. Because if the slope is significant, homework question, you automatically know that the variance that it reduced is also significant. If the slope is significant, then the amount of residual variance that is left is necessarily smaller than the amount you started with, because that's how the two models differ, empty versus predictor. So I allowed you to pay attention to only the residual variance so that you could check whether your model was right, but the rest of this was redundant. If the slope is significant, the t for that squared is the F for the model. It's a one-to-one correspondence. Likewise, if I were to calculate y hat from my one slope and correlate it with the y, the square of that correlation is r square. So the model and the slope are the same thing. This extra step is necessary whenever you are testing more than one slope at the same time. When would you need to test more than one slope at the same time? When you have a grouping variable like this. So whenever you have a categorical predictor with 3 or more levels, it takes 2 or more slopes. Whenever you want to test a nonlinear relationship with the quantitative variable, so for instance, the next example that we'll look at in here is a linear and quadratic slope to describe how age predicts income. And also when we get to the point in lecture 5 when we want to pit predictors against each other. Does, say, I'm trying to think of something. Does exposure to nicotine as an infant still predict low birth weight after you control for socioeconomic status? Like those sorts of questions where you're trying to say which predictors matter and which predictors matter uniquely. Those sorts of questions are about how the model works together are tested using this F type of idea. So this process of lumping together slopes to get their joint contribution via F and R square is a much more general idea that shows up with many specific instances. This is just your first exposure to that idea. Okay. Other questions?
So this, just to clarify, this is the same as like running an F test then. I just want to make sure I'm following.
In what context would you run your F test? Because I think you're right, but I want to make sure.
Yeah, so like looking at like 3 different groups in an experiment and trying to compare their performance on a test.
That is exactly this.
Okay, I just want to make sure because I haven't been taught F tests in this way, and this makes much more sense than just saying here's a formula, use it. So, but I just want to make sure that I'm fitting them together.
Yes, so what you just described would be called analysis of variance. And the omnibus F for the main effective group is equivalent to the F for the model when group is the only predictor in the model. So I'll say that again. Whether or not these 3 groups have different outcome means is the same thing as analysis of variance, and the F test that would give you your omnibus main effective group is the same thing as the F test for the model because group is the only predictor in the model. if I had a 3-group variable and I had another variable, let's say I added age as a covariate. What is it called if you have an ANOVA with a covariate?
ANCOVA.
ANCOVA, yeah. So in that context, there's 2 F's. Because if I wanted to know about the F for the model, that would require lumping together the 2 fixed slopes that distinguish my 3 groups and the slope for age, right? Then that's my F for the model that has 3 slopes in it. In addition to that, I might want to lump together the 2 slopes for group to talk about its contribution specifically. So the idea of an F-test is a lumping of slopes. That happens in many strategic ways. Have you heard of hierarchical regression or stepwise regression, where you have a set of predictors and then you enter another set of predictors and another set of predictors? At each step, you might ask for an F-test of the joint contribution of the new set of predictors. And that F is equivalent to asking if R squared changed significantly as you added each set of predictors. So that's yet another instance in which you do an F-test. The F-test for the model is spit out by default. The F-test for grouping variables is only spit out by default if you let the program do the dummy coding for you, but I will teach you how to ask for it. It is a statement known as test in Stata or contrast in SAS. Every software package has a way of asking for this. And yes, Emmy, to answer your question about the sums of squares, there's multiple different versions of sums of squares formulas that are developed for specific cases. Like there's a version of a formula for if you have this kind of grouping variable, and then there's another formula for if you have a grouping variable and a covariate, and then there's yet another formula if you have 2 grouping variables, and yet another formula if you have more than 1 covariate, and this is a more general, like what the model says, what's still left, and total. And so I want to just sort of focus on this as a concept, because what the model says is a more general idea that doesn't require you to know exactly how the sums of squares shake out. You can ask for sums of squares, R squares, and F's for any combination of any kind of predictors in to do whatever. The other reason that I don't spend a lot of time on sums of squares is that literally when you leave this class, if you take any of my other classes, this will not be a thing. We will go straight from sums of squares, which is known as least squares estimation, into the world of likelihood estimation, in which all of the model parameters are found through an iterative search process. So if you have a not normal outcome, can't do this. If you have repeated measures where some of the observations are missing, can't do this. If you have nested or clustered data, so non-independent data like we talked about last time, like where people show up in naturally occurring groups, can't do this. So this method of estimation is very restrictive in terms of what it allows. And the reason that it was invented is because this shit came about in like 1910 when they didn't have computers. So they could do matrix algebra back then. It took a long time, but they could do it. And so they developed these routines that could be done without computers. But modern statistics that deals with a lot more complex data structures, it can't be done this way. But the idea of asking for an F that lumps tests together, you can do that no matter what kind of estimator it goes with. So that is a concept will stay with you. All right, do I have F pictures next? Yeah, I do. I thought I did. So me F. F looks like chi-square, because F and chi-square are related to each other. F times numerator degrees of freedom is chi-square. The only difference is whether you also take into account sample size. So do you remember T versus Z? Like a long time ago, we talked about how Gossett, who worked at the Guinness Beer Factory, discovered T because Z didn't work very well for small samples. This is exactly that. So T squared is F. F generalizes to a situation in which you're testing more than one slope. T is for one slope. Both of them pay attention to sample size. Z is for testing one slope without paying attention to sample size, and z squared is chi-square. So now you've met all four. F is for testing more than one thing while paying attention to sample size. It uses both numerator and denominator degrees of freedom. So the shape of F depends on the degrees of freedom, and the critical value where the 5% area is, where the tail of where unexpected starts, that critical value depends on your degrees of freedom for both cases. So there are tables in the back of intro stat books with the F. You don't need to worry about this. The software knows. It knows what the right F should be, and it will give you an exact p-value that corresponds to that F given those degrees of freedom. So functionally speaking, you would treat it in the same way as we've done all semester. You've got a test statistic, an exact p-value that goes with it. If p is less than alpha, it's significant, reject the null. If p is greater than or equal to alpha, it is non-significant, retain the null. All right. Yeah, that's. It's like I knew it was coming. So here's the summary table. T, chi-square, z, and f. That's it. Every test statistic you're going to find is going to be one of those four. It just varies based on the context and based on your software what you get. But for the rest of this semester, it's all about T and F. T and F. I did not say anything naughty. Thank you very much. I found that the translator sometimes put words in my mouth. So, all right, other questions before we call it a day? All right, then it's Tuesday. That means I say, let me know if you need anything. Office hours at 3:15, and I'll see you Thursday. And yeah, voodoo bullshit, it said Buddha Buddha. Is it censoring me? If I say bullshit, does it say bullshit? It says bullshit? Okay, well that's good. I do want an accurate transcription. So, all right. Peace out, y'all. See you later.